The universe you were taught in school, that quiet, gentle dawn after the Big Bang, is wrong. The James Webb Space Telescope, sitting a million miles from Earth and staring back over 13 billion years, has found something genuinely terrifying in the early cosmos, and it's forcing astronomers to rethink what the first billion years of the universe actually looked like. In this video, you're going to follow that trail, step by step, and see how a few tiny, distant specks of light ended up shaking our entire story of how everything began. But before we continue, please subscribe to the channel to give your support. Let's continue. For years, you were told that this early phase, sometimes called cosmic dawn, was supposed to be relatively quiet. In the standard cosmology model, with dark matter and dark energy setting the overall rules, small clumps of matter form first. Gas falls into these dark matter halos, cools, and slowly forms the first stars and tiny proto-galaxies. In that picture, the first few 100 million years are dominated by small, faint objects building up gradually over time. You expect lots of low-mass systems, not many big, bright galaxies. Growth is meant to be step by step, starting with star clusters, then dwarf galaxies, then larger systems over billions of years. So here's the basic tension. If growth should be slow and small at the beginning, why is Webb seeing so many bright, massive candidates so early? When Webb took its first deep images, pointing at regions like the famous Hubble Deep Fields but in much redder light, astronomers immediately noticed something strange. In those pictures, at very high redshift values, there were compact, intensely bright red objects that had no right to be that luminous so soon after the Big Bang. The redshift, usually written as Z, tells you how much the universe has expanded since that light was emitted. Some of Webb's early finds cluster around redshift 7 to 9, which means you're looking at times when the universe was only about 550 to 800 million years old. Others push even further, to Z around 13 or 14, only about 280 to 330 million years after the Big Bang. From the brightness and colors of these sources, early analyses estimated that some of them could hold more than 10 billion solar masses of stars, maybe similar to the stellar mass of the Milky Way's disk today. But here's the issue. The Milky Way has had over 13 billion years to assemble. These early systems had, at most, a few 100 million years. Growing that much, that fast, is not impossible in principle, but it pushes everything to the edge of what standard star formation physics can comfortably explain. This is why you started hearing astronomers use unusual language for a scientific field that is usually careful and calm. Some researchers openly called the results troubling or terrifying. The reason is simple. If those first mass estimates had been exactly right, you would be forced to accept that galaxies can gain mass and build structure at rates that are very hard to produce in simulations based on known physics. You would need gas to fall in extremely efficiently, to cool extremely fast, and to turn into stars with almost no delay. You would also have to pack this material into very small regions, only a few thousand light years across, much smaller than the full size of the Milky Way's disk, which is about 100,000 light years across, or about 100,000 times 9.5 trillion kilometers. So the question became sharp. Did Webb actually find a problem with our basic cosmology model, or did we simply misunderstand the details of how light from these early galaxies should look? Follow-up work started to answer that. Teams went back to the data, improved the way they calibrated Webb's instruments, and built better models for how young stars, gas, and dust emit light in the infrared. They also added something that was often missing in the first rush: the contribution from actively growing black holes in the centers of these galaxies. A black hole that is pulling in gas can outshine all the stars in its host, especially in ultraviolet and X-ray light, which then gets stretched into Webb's infrared bands by cosmic expansion. When those effects were included, some of the most extreme mass estimates dropped. In many cases, what looked like a huge, ultra-massive galaxy turned out to be a combination of a more modest stellar population plus a very bright central engine. Cosmology itself, the basic dark matter plus dark energy framework, did not collapse. The expansion history of the universe, the pattern of large-scale structure, the overall model still fit the data. But this did not make the problem disappear. Even after these corrections, Webb still sees more bright, compact, high-redshift galaxies and active black holes than pre-Webb simulations predicted. The number of these objects and how luminous they are still sits above what many models were expecting. In simple terms, the early universe is more crowded, more energetic, and more efficient at building bright structures than you were taught. This is why the word terrifying still appears in discussions, not because the laws of physics are broken, but because your confidence in your own predictions took a hit. When you launch a new telescope, and within its first years you already have to retune your simulations, rethink your star formation histories, and add more aggressive black hole growth, you're forced to admit that your previous picture was too comfortable. Now the real focus shifts. If cosmology as a whole is fine, but your mental image of a slow, gentle cosmic dawn is wrong, then what exactly is filling those early images? What kind of objects are responsible for this excess of compact, red, luminous points at redshift 5, 7, 9, and beyond? Are they just dusty, intense star-forming galaxies? Or are they even more extreme, powered by black holes that grew much faster than you expected? As Webb kept staring, astronomers started grouping a specific type of these sources into one category. They're tiny in size, very red in color, and surprisingly common in deep surveys. On an image, they barely look like anything more than a dot, but their spectra and brightness tell a different story. They earned a simple nickname that sounds harmless, but the physics inside them is anything but. So here's the new tension that sets up the next step. If the early universe was supposed to be a place of small, faint proto-galaxies, why do you see it filled with these compact, ultra-red points that might be powered by young, rapidly growing black holes? What are these little red dots actually made of? And why are there so many of them? So here's the question. When you look at a tiny red speck in a James Webb image, are you seeing a normal baby galaxy, or are you looking straight at a kind of exposed engine of the early universe? Astronomers started calling these objects little red dots because that is how they first show up, a dot. Not a clear spiral, not a clear disk, just a compact red point. When you measure their size, you find that many of them are only a few hundred to maybe 1,000 light years across. In metric, that's on the order of a few hundred to about 1,000 parsecs. The Milky Way's disk is about 100,000 light years across, or about 100,000 times 9.5 trillion kilometers. So these things are smaller than 1% of our galaxy's diameter. The color is the second key clue. In a young galaxy full of fresh, hot stars, you usually expect a lot of blue and ultraviolet light. Those massive stars shine strongly at short wavelengths. Even after expansion stretches that light, you still expect the bluer filters to be fairly strong. With little red dots, you often see the opposite. The longer wavelength filters, the redder end of Webb's near-infrared range, dominate. Their spectral energy distribution rises toward the red. That's a sign that something is blocking the blue light, or something is adding extra red and infrared light. So where exactly are these things hiding in the sky? Is this just a weird glitch in one field, or is this a real population? To answer that, teams went through the big Webb surveys, SEERS, JADES, Cosmos Lab, NG Deep, and others. When astronomers went through this data with careful selection methods, they found that little red dots are not rare. A Cosmos Web analysis, for example, pulled out over 400 of them, 434 candidates in a redshift range of roughly 5 to 9. That redshift range means you're seeing them when the universe was somewhere between about 600 and 1200 million years old, and that was in a patch of sky only about 0.54 square degrees. The full moon is about half a degree pros, so we're talking about roughly the area of a few full moons packed with hundreds of these compact red sources. If you can find hundreds in such a small patch, you are very likely dealing with millions or more across the whole sky. Little red dots are not a rare curiosity. They're a common feature of the early universe that earlier telescopes just could not see clearly. Now, you might think, fine, they're small and red. Maybe they're just dusty, normal galaxies. Why is that a big deal? This is where their extreme redness becomes a problem for simple models. When astronomers fit the spectral energy distribution of a galaxy, they try to explain the observed brightness in each filter using a mix of stars of different ages, plus some dust that absorbs and re-emits light. For many normal, high redshift galaxies, you can get a decent fit with a combination of young stars, some older stars, and a modest amount of dust. With little red dots, that simple recipe often fails. To match the very strong red and infrared brightness, the models have to push the dust content to very high levels, or they have to add in a strong extra source of red light. There are basically three broad options. One, the starlight is heavily shrouded in dust, so the blue and ultraviolet are absorbed and re-radiated at longer wavelengths. Two, the stars in these systems are unusually old for that cosmic time, which would mean these objects formed their stars even earlier, pushing the problem back closer to the Big Bang. Three, a central black hole is actively feeding and dumping out huge amounts of energy, which shows up as extra red and infrared light. In many little red dots, if you do not include this active black hole component, the fits look wrong. So, how do you check if a black hole is really at work and not just hidden star formation? The answer comes from spectroscopy, splitting the light into its component wavelengths and looking for specific features. When astronomers take spectra of some little red dots, they see broad emission lines from hydrogen and helium. Broad here means the lines are smeared over a wide range of wavelengths, which corresponds to gas moving at thousands of kilometers per second, or millions of miles per hour. Gas moving that fast is almost always gas orbiting close to a massive black hole. This is the classic fingerprint of an active galactic nucleus, or AGN, where matter falling into a black hole forms a hot disk and blasts out radiation. On top of that, when you look at the shapes of these objects on the images, the light profile is extremely compact. It is dominated by a point-like core with very little extended structure visible. That is again what you expect if a bright central engine is drowning out the starlight from any surrounding galaxy. A lot of little red dots look less like small, quiet galaxies and more like bare nuclei, where the central region is doing almost all the work. This is why astronomers say these are not just boring red galaxies. A boring red galaxy would be an older system where star formation has mostly stopped, with a smoother, extended shape and no strong signs of activity. Little red dots, in contrast, often show both compact sizes and spectral signatures of extreme physics. They behave more like early, scaled-down versions of quasars or powerful AGN. So let's put this together in simple terms. In a part of the universe's history where your old picture says small, faint galaxies slowly building up, Webb is showing you hundreds of ultra-compact, heavily red, probably black hole-powered objects in just one survey field. They're tiny in physical size, intense in brightness, and statistically, there are far more of them than most pre-Webb models expected. That is the scary summary, not in the sense of danger to you, but in the sense that the early universe is far more aggressive and efficient at turning gas into bright, compact engines than you thought. If these little red dots are common, then the first billion years of cosmic time were not a quiet ramp-up. They were already full of dense regions where gravity, gas, stars, dust, and black holes were all interacting at high speed. And that raises the next key question. How far back in time do these little red dots really go? How early do they appear after the Big Bang? And what does their distance tell you about just how extreme the conditions of the young universe actually were? The strangest thing about the little red dots isn't just how they look, it's how early they show up in the universe's timeline, way earlier than your old picture of cosmic dawn can handle. When astronomers say a little red dot sits at redshift 5 or 7 or 9, that number is not just some abstract label. Redshift is basically a timestamp. The expansion of the universe stretches light, so the more the light is stretched toward the red, the longer it has been traveling, and the younger the universe was when that light left. For a lot of these little red dots, the redshifts cluster around 5 to 9. At redshift around 7, the universe is only about 770 million years old. At redshift around 9, it's down to roughly 550 million years. For reference, the current age of the universe is about 13.8 billion years. So you're looking less than the first billion years, well under the first 10% of cosmic history. If you compress the whole age of the universe into a 24-hour day, redshift 7 to 9 sits in roughly the first 30 to 40 minutes. These objects are not latecomers, they're among the first major structures you can see. So the obvious question is, how small are these things in real physical units, and how much are they actually packing into that space? When astronomers talk about size, they often use something called the effective radius, basically the radius that contains about half of the light. For high redshift compact galaxies, including many little red dot type objects, these radii are typically a few hundred parsecs. 1 parsec is about 3.26 light years, so a few hundred parsecs works out to around 1,000 light years, give or take. 1 light year is about 9.5 trillion kilometers, or about 6 trillion miles. So 1,000 light years is on the order of 10 quadrillion kilometers, roughly 6 quadrillion miles. That sounds huge in human terms, but in galaxy terms, it's tiny. The Milky Way is about 100,000 light years across, so these little red dots are maybe 1% or less of that diameter. Within that region, some models suggest you could have up to 1 billion suns worth of stars, plus a central black hole that could be millions or even hundreds of millions of times the sun's mass. You're dealing with a dense, compact core, not a big, loose disk. Now, scale that up from one object to the whole universe. Are these little red dots a rare oddity, or are they filling a significant fraction of their early cosmic volume? Big surveys like Cosmos Webb, along with Sears, JADES, and others, don't just count how many little red dots they see on the image. They also estimate a number density, basically how many of these you have per unit of cosmic volume at a given time. When you take the counts from these surveys and extrapolate beyond the small patch of sky they actually cover, you end up with a staggering result. At redshifts above about 5, there are enough LRD-type objects that over the whole observable universe, you're likely talking about millions to billions of compact, probably black hole hosting systems at those early times. That density is not what you would expect from a quiet, slow buildup of structure. If the early universe was meant to be dominated by tiny, faint dwarf galaxies, you wouldn't predict this many compact, bright red cores showing up across deep surveys. The statistics say this is a major population, not background noise. But here's the deeper problem. These things are not just numerous, they're ridiculously bright for how far away they are. At redshifts of 5 to 9 and beyond, the universe has expanded so much and the light has traveled for so long that faint objects simply drop below Webb's detection limits. The only things you can see clearly at those distances are genuinely powerful sources. Some little red dots reach ultraviolet luminosities comparable to the brightest known galaxies at similar redshifts, or even higher. When you convert that into energy output, you're in the range of about 10 to 100 trillion times the sun's power. In more technical terms, that's around 10 to the power of 45 to 10 to the power of 46 ergs per second. That energy can come from a mix of intense star formation plus accretion to a black hole. But either way, you're looking at systems running at high power. So now you have 3 facts on the table at once. They're very early, they're very compact, and they're very luminous. Early means the universe hasn't had much time to assemble them. Compact means the matter is squeezed into a small region, which pushes up densities and makes feedback from stars and black holes more violent. Luminous means they're processing gas into stars or feeding black holes at extreme rates. All of those push against the slower, smoother, build it gently over billions of years story you probably grew up with. Put this into your mental picture of cosmic dawn. The old image is a faint, smooth background of tiny galaxies gradually getting brighter. The new image, thanks to Webb and these little red dots, is much harsher. The early universe looks clumpy, full of overdense regions where gravity has already pulled in a lot of matter. Inside those regions, you're seeing compact engines, some dominated by starbursts, some likely dominated by black holes, many doing both at once. Instead of a soft glow turning up slowly, you have multiple bright red cores switching on in a relatively short window of time. This is why astronomers keep coming back to the same uncomfortable conclusion. The first billion years of the universe are not just a stretched out prologue, they're already packed with high-intensity processes. Stars are forming at rates of tens to hundreds of solar masses per year in volumes only a few hundred parsecs across. Black holes are probably growing at close to their maximum steady rates. Gas is being heated, blown out, and recycled on short timescales, all inside structures that by previous expectations should barely exist yet. So the next issue becomes unavoidable. If you have compact, extremely bright, and very common objects this early, what does that do to your standard story of galaxy growth? Can the usual picture of slow mass assembly, gentle scaling relations, and gradual buildup survive this level of early activity? Or do you have to admit that a big chunk of galaxy evolution happens in short, chaotic bursts dominated by things like the little red dots? Here's the core problem with little red dots. They don't just fill in a small gap in our galaxy story, they punch straight through the middle of it. When astronomers first looked at the reddest, brightest JWST galaxies, some early mass estimates went as high as 100 billion solar masses in stars at redshifts around 7 to 9. In words, that's a stellar mass similar to the Milky Way, but less than a billion years after the Big Bang. Later, people realized those first numbers were too extreme. They weren't fully subtracting the light from active black holes, and they were assuming smooth, steady star formation instead of short, violent bursts. Once you include those corrections, the masses drop, sometimes by factors of a few. But here's the key point. Even after you fix the models, you still end up with a population of galaxies that are too dense and too mature too early. You still have systems with billions to tens of billions of solar masses and stars squeezed into regions only a few hundred to 1,000 light years across, when the universe is only a few 100 million years old. That is a mass assembly headache, because the standard picture of structure growth says most galaxies at that time should still be in much smaller pieces. So you fixed the stellar masses a bit, but now another issue stands out. If the stars alone don't explain the brightness, what is? For a lot of little red dots, the best fits to the data require an active supermassive black hole in the center. The models that match the colors and brightness naturally give you black hole masses of around 10 million to 100 million times the mass of the Sun. That is the same ballpark as the big black holes and bright quasars seen later in the universe. But these ones are showing up when the universe is only a few % of its current age. Growing a black hole that big in that short a time is not simple. If you start with a small seed black hole from a dead massive star, maybe a few tens or hundreds of solar masses, and you want to reach 100 million solar masses in about 500 million years, you need to feed it almost constantly at close to its maximum steady rate. That maximum rate is set by something called the Eddington limit, where the outward pressure from the radiation it produces is just balanced by gravity pulling gas in. In normal language, for these early black holes, you're asking them to stay in the red zone of their fuel intake almost non-stop for hundreds of millions of years. That raises a direct question. Where does all that fuel come from in such a small region, and how does it keep flowing in without being blown away by the very radiation and winds the black hole itself creates? Even if you temporarily ignore the black hole and just look at the stars, you hit another wall, the star formation rate. To build up around 10 billion solar masses of stars by redshift 7, you need an average star formation rate of at least tens to hundreds of solar masses per year, often more. Many fits to little red dot data point to rates of tens to hundreds of suns per year. In the Milky Way today forms maybe 1 or 2 suns worth of new stars per year, spread over a disk 100,000 light years across. The little red dots are doing tens to hundreds of suns per year in a region a few thousand light years across, or even smaller. So you're not only forming stars faster, you're doing it in a far smaller volume. That means gas densities, pressures, and feedback from supernovae and stellar winds are all extreme. The system has to somehow keep pulling in fresh gas while simultaneously dealing with explosions and radiation that try to clear that gas out. You're asking the galaxy to stay in a high output mode for hundreds of millions of years without tearing itself apart or shutting itself down too early. Now look at this from the perspective of simulations. Before Webb, large cosmological simulations already tried to track gas, dark matter, stars, and black holes across billions of years. They included recipes for star formation and for feedback from supernovae and active galactic nuclei. These simulations could reproduce many broad trends of galaxy evolution, like the number of galaxies of different masses at different times. But when JWST data on little red dots arrived, some early simulations underpredicted the number of compact, bright, high redshift systems. To try to match what Webb is seeing, simulation teams had to adjust a lot of ingredients at once. They add more bursty, on-off star formation. They allow gas to flow into galaxy centers more efficiently along filaments of the cosmic web. They change how feedback from black holes couples to the surrounding gas, sometimes letting more gas reach the center before it gets heated or blown out. They tweak the initial conditions of how early halos assemble. In short, they bend their models to make objects that look more like little red dots. The fact that you have to do this much retuning only a short time after getting the first high-quality Webb data is a sign that your previous intuition about early galaxy growth was badly biased towards too calm and too slow. The simulations weren't necessarily wrong on the largest scales, but they were missing an important mode of early, compact, high-intensity growth. So why does this feel terrifying and not just interesting detail to astronomers who study galaxy formation? Because if little red dots are as common and as extreme as they appear in Webb's deep fields, then the period between roughly 300 and 1 billion years after the Big Bang is not a gentle warm-up phase. It is a violent growth spurt, with many galaxies jumping very quickly from almost nothing to dense, bright, heavily black hole-influenced cores. It means that a lot of the heavy lifting in building today's massive galaxies happened in a short, intense window that older data simply could not resolve. That shift has consequences everywhere. It changes how you think about the buildup of heavy elements, because intense early star formation and black hole activity produce and distribute metals faster. It changes how you think about reionization, because these compact engines emit huge numbers of high-energy photons. It changes how you think about the later, quiet phases of galaxy evolution, because many galaxies may be starting that quieter life having already survived an early, overpowered episode like an LRD stage. So the natural next question is simple and sharp. If these objects are forming stars this fast and feeding black holes this hard, what exactly is sitting in the middle of them, driving all of this? And how do we know it's really a black hole engine and not just extreme star formation alone? How do you know there's a black hole hiding inside something that, in the image, is basically just a red dot? The strongest clue comes from the spectrum, from how the light is spread out by wavelength. When astronomers take spectra of some little red dots, they don't just see narrow, thin emission lines from gas calmly sitting in a galaxy. They see broad hydrogen and helium lines smeared out over a huge range of wavelengths. That broadening is caused by motion. Gas is racing toward and away from you at thousands of kilometers per second, so its light is Doppler shifted across a wide band. Take a typical number that shows up in these studies, line widths of about 3,000 kilometers per second. Convert that to everyday units, and you get more than 10 million kilometers per hour, or over 6 million miles per hour. That is around 3,000 times faster than a spacecraft re-entering Earth's atmosphere, and tens of thousands of times faster than a bullet. Gas does not move that fast in normal star-forming regions. You only get those speeds when gas is orbiting very close to a massive black hole, in what's called the broad line region of an active galactic nucleus. So when you see broad hydrogen and helium lines at those speeds in a tiny high redshift source, you're basically catching the black hole in the act of feeding. Now, you might ask, could this still be a normal compact galaxy where star formation is just very intense and the spectrum is somehow tricking you? To check that, astronomers look not just at the spectrum, but at the shape of the light on the sky, the light profile. For many little red dots, the profile is almost perfectly point-like at Webb's resolution. The central pixel or two contains most of the light, and any extended structure around it is faint at best. If you try to fit a model with a central point source plus an extended galaxy, the point source usually dominates. That is exactly what you expect if you're dealing with an AGN, an active galactic nucleus, rather than a normal extended star-forming galaxy. In an AGN, the accretion disk around the black hole, plus the hot gas in its immediate surroundings, can outshine all the stars in the host galaxy in the rest frame ultraviolet and optical light. Once that light is stretched into the infrared by cosmic expansion, Webb sees a bright, compact core with very little visible host. So, in a lot of little red dots, you have two things at once: broad emission lines at thousands of kilometers per second, and a light profile dominated by a point-like core. Put together, those are textbook signatures of a black hole engine. This leads to the next step. What kind of black holes are you actually looking at in these objects? Recent analyses, including work published in top journals, interpret at least some little red dots as very young supermassive black holes, sitting in extremely dense, gas-rich environments in the early universe. Their inferred masses sit in the range of about 10 million to 100 million times the Sun's mass. That's similar to the black hole in the center of the Milky Way, which is about 4 million solar masses, and to black holes in bright quasars seen when the universe is older. The key difference is timing. These little red dot black holes are already that massive only a few 100 million years after the Big Bang. And they are not alone. Webb has also turned up signs of black hole mergers and other high redshift AGN, including a system where two black holes appear to be merging about 740 million years after the Big Bang. So the picture that forms is not one or two odd objects, but a whole environment in which massive black holes are already common and already interacting. To keep a black hole in that mass range growing and shining, it has to swallow matter at a serious rate. If you have a black hole with, say, 10 million to 100 million solar masses, and it's radiating near what's called the Eddington limit, that means the inward pull of gravity on the gas is balanced by the outward push of radiation. In that regime, the black hole can convert a few % of the mass it accretes into energy. For those masses, accreting near the Eddington rate corresponds to gobbling down up to a few solar masses of gas per year. In more intuitive terms, in gravitational energy terms, that's like eating the mass of a star like the Sun every year or two. That's not a literal one star per year event, it's a steady flow of gas equivalent to that much mass. Multiply that by millions of years, and you quickly reach tens of millions or hundreds of millions of solar masses in the black hole. The problem is, all of this is happening in regions only a few hundred to 1,000 light years across, with intense star formation happening at the same time. Gas has to flow inward through the galaxy, survive feedback from massive stars and supernovae, and then still reach the central black hole. In such a small volume, the energy from the AGN itself can heat and drive outflows that fight against fresh gas inflow. You're looking at a delicate but violent balance, where the black hole is both fueled by the galaxy and also attacking it. So when you step back and ask, what are little red dots really? The answer that fits a lot of the data is surprisingly blunt. They look less like conventional baby galaxies and more like bare engines of structure formation. They are systems where the central black hole has already grown huge, very fast, and is now blasting out enough energy to influence everything around it, from the local gas to the future growth of the host galaxy. That's the unsettling part. Instead of thinking of black holes as quiet monsters that only become important later in the galaxy's life, these objects force you to see them as active players right from the start. In the first few 100 million years, you already have compact regions where black holes are at full power, shaping their surroundings on galactic scales. And that pushes you into the next big question. If these black holes are this massive, this early, how did they get such a big head start? Did they really grow all the way up from ordinary stellar black holes? Or did some of them cheat by starting as much heavier seed black holes formed in a completely different way? How do you get a black hole that big, that early, without breaking the clock on the universe itself? One answer on the table right now is blunt. Some little red dots might be the homes of what are called direct collapse black holes. Instead of forming from the death of a star, these black holes would form directly from a huge gas cloud in the early universe. No star, no supernova, just a massive hot gas cloud that loses its support and crashes straight into a black hole. That's why people call them heavy seeds. In the normal route, you start with a very massive star, maybe tens of times the mass of the Sun. It burns through its fuel, collapses, and leaves behind a black hole of roughly a few tens or maybe around 100 solar masses. That's your seed. Now, think about the direct collapse scenario. There, the starting mass isn't 100 suns, it's more like 10,000 to a million suns right from day one. So instead of starting a marathon from the starting line, you're dropping the runner halfway up the course. This is important for one simple reason: time. The early universe doesn't give you endless time to grow supermassive black holes. From the Big Bang to redshift 7 or 8, you only have a few 100 million years to work with. If you start with a tiny seed, you need it to grow in a very aggressive, very steady way to reach 100 million or a billion solar masses. That already pushes you to near the maximum allowed steady accretion rate, the Eddington rate, almost nonstop. But if you start with a heavy seed, say 100,000 solar masses instead of 100, you've removed 3 orders of magnitude of growth from the problem. At the same Eddington rate, it's much easier to reach 10 million, 100 million, even a billion solar masses within a few 100 million years. Suddenly, the super bright quasars and little red dot like AGN you see at redshift greater than 6 look less impossible. You still need fast feeding, but you no longer need a miracle. So the next question is this just a clever idea on paper, or can the universe actually make direct collapse black holes under realistic conditions? Simulations that try to recreate the early universe have started to push hard on this. They set up regions with very low metal content, because heavy elements like carbon, oxygen, and iron make it easier for gas to cool and fragment into normal stars. In the very early universe, before many stars have lived and died, the gas is metal poor, mostly hydrogen and helium. If you also have intense radiation from nearby young galaxies, that radiation can destroy molecular hydrogen, which is normally one of the main coolants that lets gas clump and form stars. In that kind of environment, the gas is hot, metal poor, and doesn't have molecules to cool itself efficiently. Instead of breaking into many small star-forming clouds, a large amount of gas, maybe a million or more solar masses, can stay as one big hot lump. Under the right conditions, gravity wins. The lump collapses inwards, and instead of ending in a cluster of stars, a massive black hole forms directly. That's your direct collapse black hole. The simulated objects that come out of this process have properties that look a lot like what Webb sees in some little red dots. They're very compact, they're very luminous for their size, their light is dominated by a hot central source rather than a big, extended stellar disk, and their colors line up with what JWST's infrared filters pick up for at least part of the LRD population. That doesn't prove every little red dot is a DCBH system, but it shows that this channel can make things that look very similar. Now, this is not a small tweak to your galaxy formation story. It's a radical addition. Direct collapse black holes do not form just anywhere. They need very specific conditions: high gas inflow rates to keep the central region supplied, very low metallicity so the gas doesn't cool and fragment too early, and strong external radiation to keep molecules like H2 from forming and cooling the gas. That means the early universe must have had special zones, regions where the environment was just right to grow monsters fast. If those zones were rare, then DCBHs would be rare too, and they might not solve the overall population of little red dots. If those zones were common, you're looking at a universe that, very early on, was already primed to build supermassive black holes as a standard feature, not as a rare accident. That's a big conceptual shift. You're not just adjusting the rate of star formation in your models, you're opening a whole new pathway for black hole birth. Here's where the implication becomes uncomfortable. If a significant fraction of little red dots are indeed hosting direct collapse black holes, then the universe started planting heavy seeds almost as soon as it could form any structure at all. As soon as gas could clump in dark matter halos, some of those clumps didn't go into making ordinary stars and gentle proto-galaxies. They went straight into making central engines that could, within a few 100 million years, power AGN and quasars. That would mean supermassive black holes are not late-stage rare features that only appear in a few special galaxies. Instead, they would be almost inevitable outcomes of how gas and dark matter behave under the conditions of the early universe. Wherever you get the right combination of halo mass, inflow, low metals, and strong radiation, you get a heavy seed, and later, a bright AGN. maybe something that looks today like a little red dot in a JWST image. But there is another side to this debate that you can't ignore. Not every team agrees that you need direct collapsed black holes to explain little red dots. Some argue that many of these objects could be extreme, very compact starburst galaxies with huge amounts of star formation and dust, plus maybe a more modest black hole. That view doesn't remove the tension, it just shifts it. You'd still be talking about ridiculous star formation rates in very small volumes. So the tension now becomes this. Are you looking at a universe that solved its early growth problem by skipping the line and creating heavy black hole seeds, or are you looking at one that pushed normal star formation to such an extreme that it almost looks like something new? In both cases, the early universe is far more aggressive than you are comfortable with. And that sets up the next big question you have to face. If you try to get rid of the exotic, heavy seed idea and say, no, these are just galaxies with insane star formation, does that actually make things less extreme? Or does it reveal a different kind of problem hiding underneath? So let's take the conservative line for a minute and say no heavy exotic seeds, no dark stars, just normal physics pushed very hard. Can you explain a lot of little red dots that way? That's the just star formation argument. In this view, many LRDs are not primarily about black holes. They're galaxies caught in extremely intense, compact bursts of star formation, with a huge amount of dust on top. You take between 1 billion and 10 billion solar masses of young stars, you squeeze them into a region maybe a kiloparsec across, that's about 3,000 light-years across, and you surround that region with dust that absorbs the blue and ultraviolet light and re-emits it in the infrared. When you look with Webb, you see a very bright, very red, very compact source. No exotic physics needed, just a starburst turned up to maximum. On paper, that sounds more comfortable. In practice, it's not much easier. Those numbers imply star formation rates that are off the charts compared to a normal galaxy today. To reach 10 billion solar masses of stars in a short window, you're talking about making on the order of 100 to 1,000 suns per year, sustained over tens of millions of years, inside a volume only a few hundred parsecs across. A few hundred parsecs is a few hundred times 3.26 light-years, so you're dealing with something like a few hundred to 1,000 light-years in radius. Compare that to the Milky Way. Right now, our galaxy forms maybe 1 or 2 solar masses of new stars per year, spread over a disk about 100,000 light-years wide. The just starburst version of a little red dot would be forming something like a new sun every day, in a region smaller than the Milky Way's central bar. That is a difference of at least 2 orders of magnitude in intensity in a much smaller space. When you stuff that much star formation into that small a region, you don't get a quiet environment. Massive stars live fast and die young, exploding as supernovae in a few million years. Each supernova dumps huge amounts of energy into the surrounding gas, heating it and driving shocks. You also get strong stellar winds, radiation pressure, and all the usual feedback channels. The question becomes, can you keep that starburst running long enough without blowing out the gas that is feeding it? The models that try to do this have to assume very high inflow rates of cold gas from the larger scale environment, constantly refilling the region as feedback tries to empty it. The extreme redness of many LRDs fits this picture only if you assume very heavy dust. Spectroscopic studies of some confirmed high redshift red galaxies show visual extinction values of around 5 to 10 magnitudes. In simple language, that means the visible light is dimmed by factors of 100 to 10,000 by dust. Behind that dust, the star formation history often looks complex. You might have an initial intense burst of star formation, then a period where things slow down a bit, maybe partially quenched, plus some contribution from a central AGN that adds even more light at certain wavelengths. That mix can produce the kind of V-shaped spectral energy distribution that shows up in several little red dot candidates, where the brightness dips in some mid-range filters and rises again in the reddest ones. The combination of old stars, young stars, dust, and maybe an AGN gives you that shape. So a pure starburst model, if you push the parameters hard enough, can match some of the observed colors. But here's the catch. When big groups have tried to fit large samples of compact red high redshift sources, including many little red dot-like objects, they often run into the same issue. A model with only star formation plus dust doesn't fit all the details of the spectra. You can make the objects red and bright, but you have trouble matching certain lines, certain slopes, and certain features across the full wavelength range. When you allow for both strong star formation and an active black hole, the fits usually get better. One large study published in a major journal looked at exactly this question and found that for many compact red high redshift sources, you can't get away with a pure starburst or a pure AGN. You need a composite. You need a dense, intense star-forming region plus a central engine, both contributing significant light. That means the little red dots, as a population, sit in the middle between starburst only and AGN only. They're doing both. So the just star formation counterargument doesn't really let you relax. Yes, some fraction of LRDs might be dominated by starbursts with only weak or hidden AGN. Others are clearly AGN dominated. A lot of them are likely mixed cases. Either way, you're still dealing with systems that are forming stars at extreme rates in tiny regions while also growing central black holes faster than you were expecting. From your point of view, the scary part is that there is no easy way out. If you lean on exotic heavy seeds, you accept that the universe invented a fast track for black hole growth very early. If you lean on pure starbursts, you accept star formation intensities and gas inflows that almost break your feedback models. If you accept a mix, you have to handle both sets of extremes at once. That leads straight into the next disturbing piece of the story. If these little red dots are burning through gas this fast and pumping this much energy into their surroundings, what happens to them afterward? Do they calm down and become normal galaxies? Or do they burn out early and leave behind something that looks strangely old and dead in a universe that's still young? There's another uncomfortable piece of this story you have to face. What happens to these systems after they burn this hot, this early? Do they calm down? Or do they die young? Webb hasn't just found overactive, compact little red dots. It has also picked up something that, on paper, should be very rare that early in the universe: massive galaxies that are already quenched, meaning they've basically stopped forming new stars. You see these at redshifts greater than 3, when the universe is only around 2 billion years old. Some of them are heavy, with tens of billions of solar masses in stars, and their colors are red, similar to little red dots, but when you look closely at their spectra, there's very little sign of ongoing star formation. The hot blue stars that would light up the ultraviolet are mostly gone. What's left is an older, redder population and not much fresh activity. In today's universe, you expect big, dead galaxies, giant ellipticals and clusters that are done making stars. Those live in an old universe that has had over 10 billion years to evolve. Seeing something that looks old and quiet when the universe is only about 2 billion years old forces a tough question. How did they build all those stars so fast, and why did they stop so soon? A key part of the answer shows up in detailed follow-up studies that combine Webb with other instruments, like ALMA, the Atacama Large Millimeter/Submillimeter Array. One Webb plus ALMA study looked at a galaxy about 11 to 12 billion light-years away, so you're seeing it when the universe was a few billion years old. The data showed that the central black hole in that galaxy was heating and expelling the cold gas that the galaxy needed to form new stars. Gas was being pushed out at around 400 kilometers per second. That's about 250 miles per second, or roughly 1.4 million kilometers per hour, close to 900,000 miles per hour. At those speeds, the gas isn't sticking around in the central regions to cool and form new stars. It's being removed or stirred up so much that star formation chokes. That is feedback in action. The same black hole that once needed dense, cold gas to grow is now using its energy output to cut off that supply. Radiation, winds, and jets from the AGN heat the gas, drive outflows, and make it much harder for the galaxy to keep making stars. Instead of a quick, dramatic blowout where everything stops at once, you often get something slower and more persistent, a death of 1,000 cuts, where repeated feedback events gradually starve the galaxy. Each episode heats or removes a fraction of the gas, and over time, the reservoir runs low, the star formation rate drops, and the galaxy slides into a quiescent phase. Now, connect this back to little red dots. If a little red dot is a compact system with very intense star formation and a very active black hole, it is exactly the kind of environment where strong feedback can develop. In one phase, the AGN might actually help compress some gas and trigger star formation locally, but as the black hole grows and its power ramps up, the overall effect can flip from helping to killing. Gas gets heated, driven out of the central few hundred parsecs, and the fuel supply for new stars in that compact core shrinks. So one plausible evolutionary path is this. Some little red dots are the early, overdriven phases of galaxies that later show up as those massive dead systems at redshift greater than 3. First, they blaze as LRDs, compact, red, extremely bright in the infrared, with a black hole and a starburst both running near maximum. Then, over a few 100 million years, the same black hole that powered that brightness injects enough energy into the surrounding gas that star formation is cut off. The galaxy stops making new stars while the universe around it is still young. By the time you see it again, it's red not because it's dusty and active, but because it has already aged and faded. This is very different from the older, smooth growth picture many people had in mind. In that picture, galaxies sit on a nice, steady relation between their mass and their star formation rate, slowly climbing a main sequence as they gather more gas and form more stars over billions of years. Quenching, when it happens, is more of a late-stage event, after a long period of gradual growth. Little red dots and these quenched high redshift galaxies tell you that this is not the whole story. Instead, you now have to accept that some galaxies sprint through their entire active life in a short burst. They assemble a large fraction of their stars in a compact, high-intensity phase, they grow a central black hole very quickly, and then feedback from that black hole shuts things down. They go from childhood to retirement in under 1 billion years. That's fast on cosmic timescales. And this is not a rare corner case. Webb is finding enough of these early quenched systems that they have to be built into your general models of galaxy evolution. This has big consequences. It means that when you look at a massive dead elliptical galaxy today, you can't just assume it's slowly built up over a long, smooth history. Some of them may have passed through an LRD-like phase where they were tiny, insanely active, and then rapidly shut off. The relic you see now is the end state of that violent life cycle. Their stars are old, their gas is low, and their black holes are huge because the early engine phase burned through the fuel and choked off further growth. Here's the chilling thought that comes out of this. Little red dots might not just be clues about how galaxies and black holes get started. They might also be the smoking gun for how some galaxies die young. The same central engines that build up the core, light up the infrared, and drive extreme star formation are the same engines that can strangle the galaxy later by heating and expelling the very gas that made them powerful in the first place. Once you see that pattern, you have to ask a hard question about the data itself. If the stakes are this high, are we absolutely sure that we're reading Webb's results correctly? Could calibration issues, selection biases, or gravitational lensing be making these objects look more extreme than they really are? And are we overreacting to illusions created by the telescope and our own methods? So maybe you're thinking, hang on, could all of this just be Webb tricking us, and are we freaking out over calibration errors and bad models more than over real physics? That's a fair question, because those first Webb broke the universe headlines were based on very early analyses. The telescope was brand new, the calibration of its detectors was still being refined, and the models people used to turn colors and brightness into masses came from the Hubble era and stretched into new territory. Those first stellar mass estimates for high redshift galaxies, including some little red dots, came with huge error bars, even if that wasn't always obvious in the press. As teams went back and did the slower, boring work of recalibrating the instruments, adjusting the 0 points, and updating the stellar population models to better match JWST's infrared range, a lot of the most extreme numbers came down. Add in the light from active black holes that had been ignored, and many galaxies that looked impossibly massive turn into just very massive but not totally crazy. So yes, part of the initial panic was on us, not on the universe. When you correct for those issues, cosmology doesn't collapse. The dark matter plus dark energy framework still fits the background expansion and the large-scale structure. A decent chunk of the "this breaks everything" talk was an artifact of pushing old tools into a new data regime. But that's not the end of the story, because even after fixing the easy stuff, you still run into deeper problems. One big complication is gravitational lensing. When light from a very distant object passes near a massive foreground galaxy or galaxy cluster, the mass of that foreground system bends space-time and magnifies a background source. That's great for spotting extremely faint objects because lensing effectively boosts their brightness, but it also makes them look more luminous and therefore more massive than they really are, if you don't account for it. In some JWST deep fields, especially those aimed at known massive clusters, a non-trivial fraction of the ultra-bright compact sources are lensed. Once you model the lensing and figure out the magnification factor, the intrinsic luminosity of the background galaxy can drop by a factor of a few. So in some cases, the fix is literally, this galaxy is not as bright as you thought because the universe gave you a natural zoom lens. Correcting for that brings those objects closer to what your simulations can handle. Another big change came from rethinking how star formation happens over time. Many of the early mass estimates assumed star formation histories that were smooth and gradual. In those models, galaxies steadily turned gas into stars over hundreds of millions of years at a relatively stable rate. Under that assumption, if you see red colors, you often interpret them as signs of an older, more massive stellar population. But high redshift galaxies don't have to behave like that. They can form stars in violent bursts, then go quiet for a while, then burst again. If you catch a galaxy right after a strong burst, a lot of its most massive blue stars might already have died off, leaving a redder population, while the total time since the burst is still short. That can make a young, moderately massive galaxy look in broad colors like an older, more massive one built up slowly. Updated simulations and spectral energy distribution models now include this bursty behavior as standard, especially for early galaxies. When you allow for bursts plus lulls, some of the apparent need for extremely high stellar masses goes away. You can fit the same colors with less total mass and a more complicated recent history. All of that helps. Calibration fixes, better population models, lensing corrections, and bursty star formation histories together pull the most extreme mass claims back into a more reasonable range. If you stop there, you might think, okay, Webb was partly tricking us, we corrected our tools, and now everything is fine. But when survey teams redo the full statistics with all those corrections in place, a stubborn fact remains. There are still too many compact red, likely AGN hosting galaxies at high redshift compared to what pre-Webb models predicted. The exact numbers change, but the basic excess does not go away. You still see a significant population of little red dot-type objects at redshifts above 5. They're still small in physical size, still bright for their epoch, still show spectral signs of active black holes in many cases, and still appear more common than you would have expected from older simulations. In other words, the problem survived the cleanup. Webb didn't just show you artifacts, it showed you real objects that you weren't ready for. The telescope didn't break the underlying cosmology. It did expose how fragile your assumptions were about galaxy and black hole growth in the first billion years. We were too confident in smooth histories, too confident that extreme objects would be rare, and too comfortable extrapolating Hubble-era trends into a regime where we had almost no direct data. That's the unsettling conclusion. You can no longer blame this on calibration bugs, or on a few mismodeled galaxies, or on lensing alone. The little red dots are still there after every correction, after every updated model, and after every round of maybe this is just a selection effect. They are real, they're common enough to matter, and they still look weird compared to what you thought the young universe should be doing. So if the boring explanations have already been pushed as far as they can go, and the dots are still too bright, too compact, and too early, you're forced to at least look at more exotic ideas. Are we sure that all of this can be done with standard stars, dust, and black holes? Or is there a chance that some of these extreme objects are hinting at physics we haven't seen directly before, like stars powered by dark matter itself? There's an even more extreme idea on the table now, and it shows you just how far Webb's data has pushed people. Could some of these early monsters be built from a kind of star that doesn't run on normal physics, at least not the way you're used to? One proposal is the dark star. Not dark as in black hole, but dark as in powered by dark matter. In these models, the first clumps of gas collapse inside regions where dark matter is very dense. When dark matter particles interact and annihilate, they release energy. If that energy is deposited into the surrounding gas, it can heat and support the gas cloud, just like nuclear fusion does in a normal star. So instead of the star being powered by fusing hydrogen into helium in its core, it's powered, at least for a while, by the annihilation of dark matter particles. That single change has huge consequences. A normal massive star burns hot and fast. It runs out of fuel in a few million years and then explodes or collapses. A dark star in these models can keep accreting gas for much longer before it collapses, because the dark matter heating holds it up. It doesn't have to rush into fusion immediately. That means it can grow far beyond the mass of any ordinary star. Some calculations show dark stars reaching thousands to millions of solar masses. Their radii can stretch to several astronomical units across, where one astronomical unit is the distance between the Earth and the Sun, about 150 million kilometers, around 93 million miles. So now you're talking about a single star-like object that is as massive as a small galaxy's worth of normal stars, and physically as large as a mini solar system. Because of their surface temperatures and the way their energy is emitted, they would glow strongly in infrared light, right in the range JWST is built to detect. When a dark star finally runs out of whatever is supporting it, it collapses. With that much mass, the natural end state is an extremely heavy black hole, not a small stellar remnant. So dark stars, if they exist, are a very efficient way to create heavy black hole seeds early on. Instead of starting at 100 solar masses and climbing, you might start at 10,000 or a million solar masses in one go. Now, link that back to little red dots. You need massive black holes very early to explain at least some of the AGN-like LRDs and the brightest quasars at high redshift. Direct collapse black holes from gas clouds are one route. Dark stars are another, even more exotic route. In both cases, you're trying to solve the same timing problem. Not enough time to grow from tiny seeds unless you cheat by starting heavy. If dark stars were real, and if a fraction of them formed in the right kind of halos, they would collapse into heavy black holes early on. Those black holes would then sit in small host galaxies, start accreting gas, and light up as active galactic nuclei. From our point of view, billions of years later, those systems could easily look like some of the little red dots Webb's seeing, compact, very luminous in the infrared, with spectra hinting at active black holes in dense environments. The rough timing and luminosity scales line up well enough that people have started asking, are we accidentally seeing the after effects of dark stars without realizing it? Most astronomers are very cautious about this. There is no direct, unambiguous evidence yet that dark stars exist. They're a theoretical idea that could explain several JWST puzzles at once: the blue monster ultra-bright early galaxies, the little red dots, and the presence of very massive black holes only a few 100 million years after the Big Bang. But they are not the only possible explanation. Before people accept dark matter stars as real, they want to push ordinary physics as far as possible. That's why you see most teams still focusing on more conservative ingredients first: heavy dust, direct collapse gas clouds, AGN contamination, selection biases, and lensing. The rule is you only invoke exotic new physics when the data truly leaves you no choice. But the key point here is that dark stars are being discussed seriously in the literature at all. That tells you how far away from the old, simple, small galaxies gradually merging picture we've been forced to move. The fear factor here isn't dark stars are going to hurt you. It's that if something like dark stars or any similar exotic mechanism really did operate in the early universe, then the first few 100 million years weren't just a faster version of the story you already knew. They were a different regime altogether. The rules for how gas turns into light, how black holes are seeded, and how early structures assemble would be operating in ways you cannot see in the nearby universe today. In that scenario, the early universe is not just ahead of schedule, it's playing a different game. Heavy seeds from dark stars or other exotic channels would make supermassive black holes almost inevitable in dense regions. The first galaxies you see wouldn't just be scaled-down versions of modern ones, they'd be hybrid systems built out of both normal baryonic physics and dark sector processes that barely leave any trace now, except in the masses and numbers of the black holes they left behind. But even if dark stars turn out to be wrong, just having to consider them shows you how much pressure the JWST data is putting on standard ideas. You're being forced to think in terms of multiple extreme channels acting at once: heavy seeds, gas collapse, bursty star formation, AGN feedback, maybe even exotic dark matter effects, all stacked into the first billion years. And remember, little red dots are only one side of this chaos. In the same early time window, Webb is also finding incredibly bright blue star-forming systems, the so-called blue monsters. So the next question is obvious. How do these red dots and blue monsters fit together? Are they unrelated oddballs, or are they two different faces of the same violent, overbuilt early universe? You're not just dealing with little red dots in the early universe. You're dealing with a crowd. In the same time window where Webb is seeing these compact, red, probably AGN-dominated systems, it's also picking up a different kind of extreme object, the blue monsters. These are galaxies that are incredibly bright, very blue in their rest frame light, and forming stars at ridiculous rates. Same era, first few 100 million to a billion years, but very different colors. That alone tells you the early universe is not doing one single thing. It's running multiple extreme modes at once. Some teams have started to connect these two populations rather than treat them as totally separate. One line of thought is that if you have very unusual early stellar populations, for example, a top-heavy initial mass function where a larger fraction of stars are very massive, you naturally get both strong blue light from young hot stars and later strong red and infrared light from dust and AGN. Add in exotic options like dark stars as a possible extra source of infrared power, and you have a toolkit that can, in principle, explain both ultra-bright blue galaxies and heavily reddened little red dots inside the same framework. The key idea is that the color difference doesn't necessarily mean the underlying engine is different. In one case, the light you see is dominated by star formation. In the other, it's dominated by dust and black holes. A blue monster might be a system where gas is falling in, forming massive stars like crazy, but dust hasn't yet fully built up, and the AGN is either faint or not yet fully switched on in the observed wavelengths. A little red dot might be the same kind of overdense region a bit further along, where dust has grown, or where the central black hole has taken over the light budget. Different colors, same core problem. Too much gas falling in too fast in too small a volume. To test this, astronomers don't just look at single objects, they look at where these objects live. Early analyses of Webb data suggest that compact high redshift AGN candidates, including many LRDs, tend to sit in denser than average environments. They cluster more strongly than typical galaxies of the same mass. That's a hint they live in proto-clusters, early versions of the galaxy clusters we see today. If that's right, then little red dots and blue monsters are not randomly scattered. They're lighting up the nodes of the first large-scale cosmic web structures. Those environments are extreme by any standard. In metric terms, you're talking about regions hundreds of thousands of light years across, say a few hundred kiloparsecs, where the gas density is tens to hundreds of times higher than the cosmic average at that time. The gas in the larger halos can reach temperatures of millions of Kelvin, hot enough to emit X-rays. Inside that, cold streams of gas flow along filaments into the centers, feeding star formation rates from tens to thousands of solar masses per year. In more everyday terms, if a typical galaxy today is like a normal city running at regular business hours, these regions are like industrial zones, where every factory is running 24/7 at maximum output. In that kind of cosmic weather, it's not surprising that you get multiple extreme outcomes. Some halos will channel gas into large, slightly more extended regions, lighting up as blue, massive star-forming galaxies. Others will push gas straight into compact cores, where both star formation and black hole growth happen in a small volume, and dust builds up quickly, producing something that looks more like a little red dot. The physics is the same. Gravity pulling gas in along the cosmic web, cooling, fragmentation, feedback. The balance between those processes, plus viewing angle and timing, decides whether you see a blue monster or a red dot. This also changes how you think about the role of these objects in building the universe you live in now. Little red dots are not just weird dots. They are likely the early active cores of the galaxies and clusters that dominate the present-day large-scale structure. The black holes at the centers of today's big galaxies, including the one in the Milky Way, may have passed through phases that look very similar to what you're calling LRDs. Those early compact engines would have heated and stirred the gas around them, influenced where and when stars could form, and helped shape the eventual size and morphology of the galaxy. For you, this matters because it means Webb is finally resolving a regime that was basically invisible before. Hubble could see some early galaxies, but it didn't have the infrared reach or sensitivity to pick out the full mix of compact red cores, blue monsters, and their environments at these redshifts. Now, with LRDs and blue monsters both on the screen at once, you're seeing the first downtowns of the universe, the crowded hubs where matter is already concentrated, already enriched with dust and metals, already affected by black hole feedback, long before the Milky Way's gas even started to seriously collapse. So instead of thinking of little red dots as an odd footnote, you have to treat them as one face of a whole new regime of structure formation. The early universe isn't a uniform field of tiny, harmless proto-galaxies. It's a landscape of hotspots, dense regions where gas, stars, and black holes interact at extreme rates, producing both blazing blue systems and buried red engines in the same era. And once you accept that, another key question opens up. All this activity is dumping huge numbers of high-energy photons into the surrounding gas. So how much of a role do these compact engines and their blue cousins play in one of the biggest transitions in cosmic history? The moment when the universe went from a fog of neutral hydrogen to a transparent, ionized medium that light can travel through freely. How do you turn a whole universe from dark and foggy to clear and transparent when the only tools you have are stars and black holes turning on for the first time? In the first few 100 million years after the Big Bang, space is not empty and clear. It's filled with neutral hydrogen gas, atoms of hydrogen with their electrons still attached. Neutral hydrogen is very good at absorbing ultraviolet light, especially the kind of photons that can ionize it, knock the electron off the proton. So even if the first stars and galaxies light up, a lot of their UV gets swallowed by this fog before it travels very far. On large scales, the universe is basically opaque in the ultraviolet. Reionization is the name for the transition out of that state. At some point, the combined radiation from all the early stars and black holes becomes strong enough that it ionizes most of the hydrogen between galaxies. Each UV photon that is energetic enough can strip an electron from a hydrogen atom. Once that atom is ionized, it stops absorbing UV in the same way. Do this on a huge scale, everywhere, and the universe goes from a neutral UV blocking medium to a mostly ionized, transparent one. That is what people mean by turning the lights on. The big questions have always been, when exactly did this happen, and who did most of the work? Normal stars or something more extreme? This is where Webb starts to change the game, because it can see galaxies at redshifts well beyond what Hubble could reach, into the era when reionization was underway or just starting. JWST has already confirmed galaxies at redshift greater than about 13, which means you're seeing them only around 330 million years after the Big Bang. One well-known example is JADE's GS Z13-1. At that time, by old expectations, you might think the universe should still be mostly neutral, with only small pockets of ionized gas. Instead, the UV light from this object seems to have carved out a local bubble, a region around it where the hydrogen is already ionized enough that its light can escape to us. That suggests that reionization is starting earlier and maybe more patchy and aggressive than many older models assumed. You're not getting a smooth, slow fade of the fog. You're getting bubbles, holes punched into the neutral gas by groups of bright sources. Some of those will be intense, compact star-forming galaxies. Others might be exactly the kind of AGN-powered systems we're calling little red dots. So what role do LRDs play here? Are they just side characters, or are they key contributors to this clearing the fog process? If a large fraction of little red dots are hosting active galactic nuclei, they're producing a lot of high-energy photons, not just UV, but also soft X-rays. These photons are especially good at ionizing hydrogen because they can travel further through the gas before being absorbed. A universe that is littered with compact AGN hosting systems at redshifts between about 5 and 9 will naturally produce a strong background of ionizing radiation. On top of that, the intense starbursts in some LRDs are producing massive hot stars that also emit huge amounts of UV. So each little red dot can act as a local engine, both heating and ionizing the gas in and around its host halo. The crucial trade-off here is efficiency versus brute force. Normal massive stars, especially O-type stars, are very good at pumping out ionizing UV photons, but each individual star isn't that powerful. You need billions of them spread across many galaxies to have a significant effect on the whole universe. A single supermassive black hole, actively accreting at near its maximum steady rate, can condense that output into one compact source. Take a black hole with about 100 million times the mass of the Sun. If it's accreting at close to the Eddington rate, it can emit as much ionizing radiation as billions of O-type stars combined. So instead of needing a whole galaxy's worth of massive stars acting together, one AGN can, in principle, do the same job from a small central region a few light days or light weeks across, which is tiny compared to a galaxy's full size. Now, imagine that even a modest fraction of the little red dot population at redshifts 5 to 9 hosts this kind of black hole. Not all of them have to be in the 100 million solar mass range. Even 10 million solar mass black holes contribute a lot. When you add up their output across the volume of the early universe, you get a non-trivial contribution to the total budget of ionizing photons. That means reionization might not be driven only or even mainly by normal star-forming galaxies. It might be significantly boosted by compact AGN, the same engines that make little red dots strange in the first place. This doesn't mean stars are irrelevant. Normal galaxies with just intense star formation are definitely part of the picture. The point is, you can't ignore the AGN anymore. If your early universe is full of little red dots and a healthy share of them are powered by growing black holes, then those black holes are almost certainly helping to reionize their surroundings. They're turning gravitational energy, gas falling into a deep potential well, into radiation that can strip electrons off hydrogen over large distances. Put all of this together and you get a reionization picture that is much sharper and much more violent than the simple soft dawn story you might have heard before. The fog doesn't just thin out because of a gentle glow from countless tiny galaxies. It gets ripped open by concentrated sources, compact starburst cores, and AGN drilling ionized tunnels through the neutral hydrogen. Instead of a slow, uniform transition, you have a network of bubbles that grow, overlap, and eventually fill space. In that sense, little red dots are not just weird objects sitting in the background. They may be central tools in this phase change. They're the blowtorches, taking gas that would otherwise block UV light and turning it into transparent plasma. And it's happening at a time when the universe is still young, less than 1 billion years old, when your old models were comfortable with mostly neutral conditions. That leads to a natural and slightly disturbing follow-up. If these compact engines were so common and so powerful early on, where did they all go? They're not swarming all over the sky at later times. By the time you get to redshift 2 or 3, a lot of the universe's volume looks calmer. So what happened to these early, overdriven systems? Did they just fade? Did they merge? Or did they transform into something we now see in a very different form? By the time you get to what astronomers call cosmic noon, the heyday of star formation around redshift 2 to 3, something big has changed. The sky is not full of little red dots anymore. Observations and simulations both point to the same pattern. At redshift above about 5, so when the universe is younger than about 1.2 billion years, LRD-type objects are common in deep JWST fields. By redshift 2 to 3, when the universe is around 3 billion years old, those compact ultra-red AGN-like points are rare. The overall number of bright galaxies has gone up, structures have grown, clusters are forming, but the very specific, tiny, hyper-compact, over-red core population has mostly thinned out. That tells you something dramatic happens to a lot of these systems over just a couple of billion years. So the obvious question is, what are their likely fates? How do you take a small, brutal little core and turn it into the kind of galaxy you see more often later? One route is straightforward: merging. A little red dot is compact, but it doesn't live in isolation. It's usually sitting in a dense environment, surrounded by other galaxies and smaller halos. Over time, gravity pulls them together. The LRD can merge with other galaxies, dragging its massive black hole and dense stellar core into the center of a growing system. The end result is a galaxy with a very compact central bulge, the kind you see in massive ellipticals today. In that picture, the LRD is basically the seed bulge that gets built around, not the final galaxy itself. Another path is to push the AGN phase even further. If the central black hole in an LRD keeps accreting at high rates as the host grows, it can transition from a compact, moderately bright AGN into a full-blown quasar. In that phase, the black hole's radiation and outflows get powerful enough to blow out much of the gas in the central region, often across tens of thousands of light years. Once that happens, the galaxy's fuel tank is partly emptied, star formation slows or stops, and the quasar eventually fades as the accretion rate drops. What's left behind is a big black hole and a heated, gas-poor galaxy. A third outcome is more gradual but just as final. Strong feedback from stars and the AGN slowly quenches star formation. The gas in the central few hundred parsecs gets heated, stirred, and pushed around repeatedly. Some of it escapes the galaxy's central potential well, some of it is pushed into the halo where it stays hot for a long time. Over hundreds of millions of years, the cold gas reservoir shrinks. The star formation rate drops from hundreds of solar masses per year to tens, to 1 or less. The galaxy doesn't suddenly explode or tear apart, it just runs out of usable fuel and settles into being a red, dead core embedded in a larger halo. You also have to think about what happens when the black holes themselves merge. In dense environments, galaxies merging is common, and when galaxies with central black holes merge, the black holes can form binaries. One theoretical study looked at exactly these kinds of compact systems and asked, what do supermassive black hole binaries do to their host structure? The answer is potentially a lot. As a binary black hole orbits in the center, it can slingshot stars out of the core region, carving out a lower density center. It can also stir and redistribute gas, changing where and how stars can form. Over time, this process can transform a tight, very compact core into something that looks more like the smoother central regions of massive galaxies today. The timescales for all of this is short compared to the age of the universe, because these systems are small and fast inside. If a typical LRD is only a few hundred parsecs across, say a few hundred times 3.26 light years, and the stars in it move at a few hundred kilometers per second, the time for a star to cross from one side to the other is only a few million years. For example, 300 kilometers per second is about 1.1 million kilometers per hour, around 700,000 miles per hour. At that speed, crossing a few hundred light years takes on the order of a few million years. That dynamical time is the fundamental clock for how quickly the system can rearrange itself. Now stack a few hundred million years on top of that. In that interval, stars can orbit the center dozens of times. Gas can flow in, form stars, get blasted out, cool, and flow back in. Black holes can spiral together and merge. Galaxy encounters can disturb or disrupt the compact core. You don't need the whole age of the universe to radically change an LNRD. A few 100 million years is enough to completely reshape it. By the time you get to redshift 2 or 3, many of those original little red dots will have gone through several cycles of this kind of dynamical violence. What you see at that stage are more familiar-looking objects, massive ellipticals with dense central bulges, quasars in larger hosts, and quenched galaxies sitting in groups and clusters. The LRD phase is brief and intense, which is why you see it clearly only in that earlier window. Later, the descendants are still there, but they look very different. For today's universe, the implication is pretty direct. The supermassive black holes sitting in the centers of present-day galaxies, including the one in the Milky Way, probably did not grow slowly and politely over 13 billion years. At least some of them likely went through phases that looked a lot like little red dots, or even more extreme. In their teenage years, they would have been in tiny, gas-rich, overcrowded systems, accreting rapidly, throwing off radiation and winds, and strongly influencing their surroundings. When you see the calm-looking bulge of a nearby galaxy now, you're seeing the aftermath of that story, not the story itself. The violent growth phase has passed, the gas has been consumed or blown out, and the black hole has settled into a lower activity state. Little red dots are your snapshot of that missing phase, the part you never had direct data on before JWST. So you're left with a new picture, where black holes and galaxies don't just quietly co-evolve on slow, smooth tracks. They go through short, intense, transformative stages that are easy to miss unless you have a telescope that can see deep into the early universe in the right wavelengths. The next challenge is clear. If you want to prove this story and fill in the details, you need to catch these systems in as many different kinds of light as possible and watch for their fingerprints in more than just infrared images. That's where X-rays, millimeter waves, future infrared surveys, and even gravitational waves come in. And they're going to tell you whether your LRD story is complete or whether there's still something even stranger hiding in those tiny red points. Right now, Webb has shown you the dots, but on its own, it can't finish the story of what they really are or how far they push physics. The next step is to hit the little red dots from every angle you possibly can, in as many wavelengths as you can. JWST owns the infrared, but it can't tell you everything about hot gas right next to a black hole or cold gas sitting tens of thousands of light years out. That's where X-ray observatories and millimeter arrays come in. If a little red dot really hosts an actively feeding black hole, it should be shining in X-rays, because the hottest, innermost parts of the accretion flow produce very energetic photons. Telescopes like Chandra and future X-ray missions can point at JWST fields and look for faint X-ray sources lined up with LRDs. A detection there is basically a direct, yes, there is an accreting black hole here. At the other end, millimeter arrays like ALMA focus on cold gas and dust. They don't care about hot accretion disks. They trace the raw fuel supply, molecular gas, and dust clouds at temperatures from a few tens to a few hundred Kelvin. If you point ALMA at a little red dot and you see a huge reservoir of cold gas wrapped around it, you know it has plenty of fuel left to keep feeding both star formation and the central black hole. If instead you see that the cold gas has already been depleted or blown out, you're catching the system late in its life, maybe on its way to quenching. Combining JWST's infrared snapshot, Chandra's X-rays, and ALMA's gas and dust map gives you a full energy budget, from cold inflows to hot outflows. But you also need more sky. Webb is powerful but slow. Its deep fields cover tiny patches. To really understand how common little red dots are and how they cluster, you need wide surveys. That's where the Nancy Grace Roman Space Telescope comes in. Roman will survey large areas of sky in the infrared, not as deep as JWST, but far wider. That means it can catch little red dots by the thousands instead of by the hundreds, and map the environments they live in. Are they always in overdense regions, protoclusters, or do some live in more isolated halos? Roman will give you the statistics you need to answer that. On the ground, the next generation of 30-meter class telescopes like the ELT, TMT, and GMT will do surgery on individual systems. With their huge mirrors and adaptive optics, they'll be able to resolve structures on scales of a few hundred parsecs in high redshift galaxies. That's a few hundred times 3.26 light years, so still tiny in cosmic terms, but big enough to separate the central core from its immediate surroundings. They'll measure internal motions, velocities of a few hundred kilometers per second, hundreds of thousands of miles per hour across those small regions. From that, you can infer how much mass is packed into the center, how steep the gravitational potential is, and whether the stars and gas are rotating, inflowing, or being kicked out. If little red dots really host big black holes, some of those black holes are going to merge. Gas-rich, compact systems in dense environments collide. Their central black holes sink to the middle via dynamical friction, form binaries, and eventually coalesce. When that happens, the system emits gravitational waves, ripples in space-time. Future space-based detectors like LISA are designed to be sensitive to mergers of black holes in the range of roughly 10,000 to a million solar masses at high redshift. That's right in the heavy seed regime people talk about for DCBHs and dark star remnants. If LISA starts picking up a population of HRZ black hole mergers in that mass range, you've got direct, independent evidence that massive seeds really existed and were common enough to bump into each other. So while current telescopes are giving you images and spectra, future gravitational wave observations will be giving you a merger history. Those two together will tell you if the growth path you're inferring from light actually matches the growth path written into the fabric of space-time itself. On the theory side, nobody's sitting still either. The old models that assumed smooth star formation histories and normal stellar populations are already being upgraded. Researchers are building simulations and SED models that allow for top-heavy initial mass functions, where very massive stars are more common than they are today. They're adding in exotic stellar populations, like hypothetical dark stars, as test cases. They're also complicating the dust, not just a single uniform dust screen, but clumpy and patchy dust geometries that can hide some regions and reveal others, changing the observed colors in subtle ways. All of that feeds back into how you interpret little red dots, blue monsters, and early quenched galaxies. If your model treats dust too simply, you might overestimate age or mass. If your stellar populations are wrong, you might misinterpret a top-heavy burst as an older, more massive system. If your AGN templates are off, you might underestimate the black hole contribution. So people are iterating, run simulations with more realistic physics, generate mock observations, and see if they produce objects that look like little red dots in JWST filters. The stakes in all this are high. Little red dots are not a minor puzzle you can push to the appendix of cosmology. They force you to design instruments, simulations, and data pipelines under a new assumption. The early universe is busy, not boring. It's full of compact engines, fast black hole growth, violent starbursts, and rapid quenching, all happening inside the first billion years. Every new telescope that comes online from now on is, in a sense, a test of that assumption. Roman, the ELT, TMT, GMT, LISA, next-generation X-ray missions, they'll either confirm that the early universe really was this wild, or they'll show that we're still missing a piece and that some of what you're seeing in LRDs is only part of an even stranger picture. And that leads to the last thing you have to confront. Once you've gone through all the panic, the corrections, the exotic ideas, and the upcoming tests, what are you actually supposed to take away from the little red dots about how the universe works and how wrong your original mental picture really was? Here's the bottom line. The little red dots didn't kill physics, but they did kill the comfortable version of the early universe you grew up with. After the first wave of panic, once people fixed the calibration, added AGN light, and updated the models, one thing became clear. The basic lambda CDM picture still holds. The way the universe expands, the role of dark matter in building large-scale structure, the overall framework, all of that still matches the data. You don't have to throw out the idea of dark energy, or the cosmic microwave background, or the way gravity works on big scales. The universe is not trolling you with a completely different set of rules. But inside that framework, in the details of how galaxies and black holes grow, you were far too relaxed. JWST and the little red dots are telling you that growth is much more extreme and much more front-loaded than your old mental picture allowed. A lot of the serious building work is happening early, fast, and in small, dense regions, not slowly and gently spread over the whole 13.8 billion years. Look at what is already in place by just a few 100 million years after the Big Bang. You have galaxies as bright as some of the brightest things you see at later times, shining hard in ultraviolet and infrared. You have black holes with masses of millions to hundreds of millions of suns, sitting in the centers of small, compact hosts. You have these red, dusty, ultra-compact systems, the little red dots, putting out as much energy as whole modern galaxies, while being only about 1,000 light-years across, which is roughly 9.5 quadrillion kilometers, around 6 quadrillion miles. None of that fits the old, tiny, faint proto-galaxies only story. So your idea of galaxy evolution has to change. The neat textbook story was that small things form first, they merge into bigger things, and over billions of years you end up with large spirals and ellipticals. That sequence is not wrong, but it is only half the story. The other half is a much more abrupt mode, where some regions go from almost nothing to a dense, overpressurized core extremely quickly. They jump into a phase of intense star formation, rapid black hole fueling, and then often quench or transform in relatively short timescales, hundreds of millions of years, not billions. Webb is showing you that these short, violent phases are not rare special cases. They're a standard piece of how big structures and big black holes assemble. There's a flashbang mode of evolution that you were missing because you couldn't see it before. Little red dots, blue monsters, and early dead galaxies all sit in that regime. It helps to put some numbers on this so it doesn't stay abstract. Take the black holes. You're dealing with objects that can grow by up to a few solar masses per year in the early universe. That means gas equivalent to 1 or 2 suns every year falling into the central engine and being converted partly into radiation. Over tens of millions of years, that builds up to tens of millions of solar masses. Over hundreds of millions of years, you can reach the 100 million solar mass range. That's why you can plausibly get big AGN and quasars so early, as long as the feeding is efficient and often close to the maximum allowed steady rate. Now look at the gas that doesn't make it into the black hole. Feedback from the AGN and from massive stars can drive outflows at a few hundred kilometers per second. We're talking roughly 400 kilometers per second in some observed systems, which is about 900,000 miles per hour. That's fast enough to move gas out of the central kiloparsec in a few million years. If that gas leaves the star-forming region and doesn't cool and fall back quickly, it's gone as fuel. That's how you take a galaxy from forming hundreds of solar masses of stars per year to forming almost none on a timescale shorter than the gap between some major events in Earth's own history. The scales are just as extreme. A typical compact core in these high redshift systems might be a few hundred parsecs across. A parsec is about 3.26 light-years, so a few hundred parsecs is around 1,000 light-years. That's a tiny fraction of a big galaxy size, but in that volume you can have billions of stars, plus a central black hole, plus dense gas, plus dust. If you tried to cross one of these regions in a modern passenger jet, flying at around 900 kilometers an hour, roughly 560 miles per hour, you would need longer than human civilization has existed to get from one side to the other. And that's just crossing the core, not the whole galaxy. When you hear astronomers call this terrifying, they're not talking about danger to you personally. They're talking about how far off their own story was. For years, the default mental picture was a calm ramp-up, small galaxies tinkering along and slowly building bigger ones. The data now shows a universe that wasted almost no time. Within its first billion years, it already had regions where everything was overclocked. Gas falling in at extreme rates, stars forming at rates of tens to thousands of solar masses per year, black holes in the 10 million to 100 million solar mass range, feedback driving gas out at hundreds of kilometers per second, and systems going from birth to burnout in under a billion years. Little red dots sit right at the center of that new picture. They are the visible markers of those extremes, where star formation, black hole growth, dust buildup, and feedback are all happening in very small, very young objects. They show you the early cores that will later become the bulges of big galaxies, or the remnants of quenched systems, or the seeds of massive clusters. They're not a glitch in the data. They're a window into a phase of cosmic history you didn't have direct access to before JWST. And here's the key point you should carry out of all this. The universe did not change to match your expectations. Your expectations have to match the universe. Basic gravity, dark matter, and dark energy still set the stage, but the script playing out on that stage is sharper, faster, and more chaotic than the old story suggested. The early universe is full of starving and overfed galaxies, rapid mergers, early deaths, and central black holes that are far from passive passengers. They're running the show from very early on. You're still at the beginning of understanding what those tiny red points are hiding. As more X-ray data comes in, as ALMA maps more gas, as 30-meter telescopes resolve the dynamics, and as gravitational wave detectors start listening to early black hole mergers, that picture will sharpen. The odds are high that some of your current best guesses about LRDs will need to be revised again. But that's the real impact of the little red dots. They force you to accept that the safest assumption about the early universe is no longer it was boring. The safest assumption now is it was busy, and every new observation is a test of just how far that busyness goes. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.